In this video, I'm going to show you how to solve the ALEKS problem called calculating solubility. This problem actually makes me really sad. There are a lot of different versions of this problem and they all look pretty different from one another. I am actually going to solve 6 versions of the problem in this video, which I think is a record for me. And there are probably more versions of the problems than the 6 that I'm going to solve, but I'm hoping that watching me solve the 6 versions of the problem will give you enough guidance that you'll be able to tackle whatever problem ALEKS gives you. So all of the versions of the problem are ultimately asking you the same 2 questions. They just vary in terms of the scenario or the story. The 2 questions that you're going to be asked is, number 1, whether or not you can calculate the solubility of a particular solution. And then if you can calculate the solubility, ALEKS wants you to do that. So the first thing that we need to think about is, what is solubility? Solubility is the grams of solute that are dissolved in volume of solution, and the units that we typically use for solubility are grams per milliliter. And this is the grams of solute per milliliters of solution for a saturated solution. So not just for any solution, it has to be a saturated solution. What does it mean to be a saturated solution? That means that we have the maximum amount of solute dissolved in the solution. So in order for us to be able to calculate the solubility from the information in the problem, we have to be dealing with a solution that is saturated. We have to know that the solution is saturated, and that's the part that makes this ALEKS problem tricky. Calculating solubility just in itself is not hard. It's just grams divided by milliliters. That's not tricky. The tricky part is reading this scenario and knowing whether or not the solution is saturated. So there's a few hints or a few things that I'm going to have you look for to help you decide if your solution is saturated or not. Now, this particular version of the problem, it tells us that we have a 5 milliliter sample of water. If our solution is saturated, that's going to be the volume. And it says that it is taken out of a pool that is lined with crystals. And if we see that word crystals, that is a pretty strong hint that the solution is actually saturated. I don't think it's a guarantee, but it's pretty sure that it's saturated. And then it tells us that this sample goes back to the lab, it gets filtered so that the crystals are removed, and then all the water gets evaporated, crystals are left behind, and they weigh 0.75 grams. Okay, so what we had in this scenario was this pool, so I'm just going to draw it as a beaker, of solution, and there were crystals growing inside of this solution, and the presence of the crystals growing inside of the solution tells us that the solution itself is definitely saturated. The presence of the crystals tells us that there was at one point an excess of solute in that solution, and that we know for sure that the solution is saturated. So since we know for sure that the solution is saturated, we can take our data here and plug it into the solubility equation. First of all, yes, we can calculate the solubility of this compound, and that solubility is going to be 0.750 grams divided by 5 milliliters. And I'm just going to do that math on a calculator that I have off to the side. 0.75 divided by 5 to 2 significant figures is 0.15. And then don't forget, ALEKS is going to want you to include your units here, which is grams per milliliter. So that one wasn't too bad. Let's take a look at another version. This one is telling us that we have 350 milliliters of solution, and there is a certain amount of X dissolved in it, and that a student sees a precipitate has formed. So if we see the word precipitate, that, like crystals, is another indication, another hint that the solution is saturated. It's not a guarantee saturated. It's not a guarantee that the solution is saturated. We can't just focus on the word. We have to think about how the word is being used in the problem. But if we see that a precipitate is formed, that is very similar to a crystal. So the liquid is transferred to a beaker, throw away, evaporate the water, the 16.016 kilograms. So this is really weird wording on this problem. I don't love the wording of this problem. But let's try to draw a picture and see what's going on. So we have 350 milliliters of a solution, and that solution is cooled down. A precipitate is formed, so we get that chunky stuff forming down at the bottom, and then that liquid, in this case, then yes, this solution is saturated. So again, anytime we have a situation where we have a solution and there's some sort of solid, whether it's being called a precipitate or whether it's being called crystals, that tells us that that solution is saturated. So I'm struggling with the way that this problem is worded. Our solubility is, first of all, yes, we can calculate the solubility. Solubility is going to be grams per milliliter, and that's going to be this 0.016 kilograms, so that would be 16 grams. And I think that is referring to the mass of the solute, but it's just really not clear in this problem. So I'm hesitating because the wording is just so funky. It weighs 0.016 kilograms. It what, Alex? It what? The beaker? The water? What? All I know is that yes, we can calculate the solubility in this situation, and since there's only one mass and only one volume, then my assumption is that this is how we're going to solve the problem. But man, I really don't like that last sentence. This is really stressing me out. Okay, so 16 kilograms, that is the same as 16 grams. We're just going to go 0.016, multiply that by 1,000. That's 16 grams per milliliter. And honestly, you could probably just keep this in kilograms per milliliter, but I don't know exactly if ALEKS is okay with that or not, and you just don't want to test ALEKS like that. 0.046 grams per milliliter, two sig figs. Okay, moving on. The next version of this problem. This says we have an unknown solid, a quantity of an unknown solid to 600 milliliters. That's going to be our volume. After 10 minutes of stirring, all of that has dissolved. Drain the solution, evaporate the water. The precipitate is left behind. And that precipitate weighs 0.12 kilograms. Okay, so we've got a beaker, and it's got 600 milliliters of water in it, and we added some solute, and then it says all of it dissolves. And then it says you drain off the solution. Drain it. Why? Drain the solution and evaporate the water. And that causes a precipitate to be left behind. But at no point in this problem, at no point is it telling us that we have a solid or a precipitate or crystals in a solution. It does tell us that there's a precipitate left behind, but if we read carefully, nowhere in here is it telling us that we have liquid coexisting with crystals or a liquid coexisting with precipitate. So this, I'm going to say, is a no. We can't calculate the solubility. All of the X has dissolved. That is most likely indicating that the solution is not saturated. A saturated solution is going to be one where it doesn't all dissolve, and we know that because it's got like crystals left behind, or a precipitate is forming while we're making the solution. But again, this is funky wording. Okay, so this problem makes me so sad, but I'm pretty sure that that's going to be a no, because we never have liquid coexisting with crystals. Okay, moving on. This problem's really stressed me out. We have a volume, 33 milliliters, from a rock pool lined with crystals. So that saturated. We have water saturated. We have a pool of water lined with crystals. We have that coexisting water with the crystals at the same time. Okay, Oh, but then this problem gets tricky. So they took the sample and then they diluted it to a different volume, and then the crystals are 5 grams. So first of all, yes, we can calculate the solubility because we've got crystals coexisting in this with this solution. We definitely have a mass of 5 grams, there's no doubt about that, but we have two different volumes that we have to deal with in this problem. We have 33 milliliters and then we have 350 milliliters. The volume that we want to use is the original volume, the 33 milliliters. We do not want this whole diluting the sample with distilled water. That when we dilute that sample, we are probably turning it into an unsaturated solution. But either way, we want to calculate the solubility of the original solution, that 33 milliliter original sample. So let's do the math on that. 5 divided by 33 is 0.15 grams per milliliter. Let's see if there's more. There is more. Oh man, okay. Here we have 77.1 grams, 2 liters. After 10 minutes, only some of it has dissolved. So that means that the solution is saturated, again, because it's not completely dissolving, because we have some solid in the liquid. Solid in the liquid means that it's saturated. Crystals in the liquid mean it's saturated. Precipitate in the liquid means it's saturated. Okay, so then it says we've got another mass here. Washes, dries, the X that did not dissolve weighs 23.1 grams. Our solubility is grams per milliliter, and that is the grams of the solute, specifically the grams of solute that dissolved, divided by the milliliters of the solution. So we can see that we started with 77.1 grams original. That's how much we put in there originally. And then the amount that did not dissolve was 23.1 undissolved. And that's going to tell us how much actually dissolved. That's the number that we want to use to calculate our solubility. 54 grams per 2 liters of solution, or 2,000 milliliters. Again, you can probably use the liter unit, but I'm not going to risk it. 54 divided by 2,000 is 0.027 grams per milliliter. Oh, to 3 significant figures, 0.0270 grams per milliliter. Maybe that was the last one. Oh no, there's one more. Okay, this is the last one that I'm going to do for you. Here we have 0.12 kilograms, 4 liters of water. All of the X has dissolved, not saturated, because it all dissolved. Just to be sure, the student adds some more X and it also dissolves. If it's dissolving, not saturated. So this is a no, we cannot calculate solubility. You can't calculate the solubility when everything dissolves. There has to be some undissolved or crystals or a precipitate. I am so sorry that somebody assigned this problem for you to do. This is a really difficult problem. Hang in there.